Cut.
So good afternoon, everyone. My name is Attila Nagy, and today I'm going to present this talk on automatic punctuation restoration with BERT models on behalf of my co-authors. So let's dive into it. So before talking about how we actually solve this problem, I think it's worth talking about why do we even care about having punctuations. So typically the most straightforward industry use case is the output of ASR systems, which typically output unsegmented transcripts. And we want to put punctuations in these texts. And the reason for this is twofold. So first of all, it affects readability as much as having a pretty significant error rate. And also if we wanted to do some kind of downstream NLP task on these corpora, then having punctuations could significantly improve this as well. And I listed a few examples here. For example, NMT, sentiment analysis, or information extraction are just a few. So how do we approach this problem? So typically, ASR systems output two kinds of features, lexical features and prosodic features. And if we wanted to build like a really cutting edge system, we would use both of these features and combine them in some kind of ensemble model. But due to the nature of how these ensemble models work, it makes sense to try to improve these models individually. So what we're doing in this work is we're only focusing on lexical features and we're ignoring prosodic features. So a few words about related work on textual features. So these features were, whoops, someone's requesting control. Hold on. Okay, so can you see my screen?
Yes, I don't know what happened, okay. But we can see.
Yeah, no problem. So where was I? Yeah, so the field was primarily dominated by recurrent neural nets, which was very recently outperformed by the transformer architecture and BERT in particular. So the current state of the art in this field is a variation of BERT, which uses aggregated predictions in its output, which I'm going to talk about because we take a very same approach in our work. So our contributions are twofold. We work on two languages, English and Hungarian. So for English, we re-implemented this state-of-the-art model. We evaluated it on a benchmark dataset. This is the TED Talks dataset that is very commonly used in the literature. And there hasn't been an open source implementation for this paper, and we open sourced our code, so this is our contribution here. And for Hungarian, we applied the very same model on the Szeged Tree-Bank dataset, where we apply certain transformations on this data to generate an ASR-like format. And obviously, we had to use a different BERT model. We picked the multi-long BERT and HuBERT. And as far as we know, there hasn't been work on automatic punctuation restoration for Hungarian using BERT models. So the way we formulate this problem is considering it a sequence labeling task with 4 target classes. These are empty, comma, period, and question. So the reason for not including more is that the frequency of other punctuation marks, such as exclamation marks, for example, are very low in the majority of the corpuses and the ones we work with as well. So it wouldn't have been feasible to include those. And for this reason as well, we apply conversions where it semantically made sense. So for example, we converted exclamation marks and semicolons to periods, quotation marks to commas. We removed introvert hyphens. And if the hyphens were between white spaces, we converted them to commas. And it's also important to mention that we had to mask word internal tokens because it was mentioned in, I think, the previous presentation that BERT uses sub-word tokens. And we only want to predict punctuations after the end of every word. So we don't predict word punctuations between word internal tokens. So that's something we have to take care about. So this is an example of how a sentence looks like in different parts of our pipeline. So we have our original sentence. And if we look at the pre-processed variation, we see that the text has been lowercased. And also we have some conversions in the punctuations as well. And this is what I mentioned, that the word Tyrannosaurus is tokenized to 3 different tokens with BERT's tokenizer. But we only want to predict a punctuation for the very last token of the sequence of tokens. Okay, so for English, as I said, we are using the TED Talks dataset, which contains about 1,000 unique transcripts of TED Talks. This is about 2.4 million words. And originally, this was a competition which had an official train-valid test split. So for the sake of reproducibility, we used this train test split. And you can see the distribution of labels here in each of the data sets. And you can see that there is a pretty high unbalance in terms of the distribution of classes. For Hungarian, we are using the Szeged tree-bank dataset, which is a gold standard. Oops, it's happening again. Okay. So this is a gold standard dataset, which contains a variety of different domains, such as fiction, news articles, or legal text. And if you think about it, these different subcorpora have very different punctuation distributions. So we couldn't really do the train-valid test split properly because, for example, in our first experiments, the test set contained, like, for example, 3 question marks. So what we did is we merged all the subcorpora and we shuffled the sentences. So obviously this does introduce a bias in the prediction of periods because BERT is capable of recognizing the context change. But we had to take this trade-off because this way we could predict question marks as well. So this is our architecture. So this is a pretty standard setup for sequence labeling with BERT. So we take an input sequence and we are going to tokenize it with BERT's tokenizer. BERT's going to receive a sequence of tokens with a length of 512, and it's going to output a hidden embedding vector for every one of these tokens. And these vectors are going to be passed on to a classifier module, which is the same in every time step. So this has shared parameters. And this is just a feed for neural networks with 2 hidden layers and dropout included. Okay, so as I mentioned, we're aggregating predictions in the final output. And I'm going to explain how this works. So as I said, BERT takes sequences of 512. But if you think about it, we have our huge blob of text, which is the whole data set. And we don't necessarily have to pass these sequences one by one. We can pass it on such that they're going to overlap. So we're going to get multiple predictions for the same token with using a different context. And the number of predictions we get for a token depends on the size of this basically shifting window. And this is something we're going to optimize on the validation set. And in the end, if we have multiple probability distributions for a token, we're just going to take their class-wise averages and we're going to output the argmax. Okay, so the training details. We used AdamW as an optimizer. We used gradient clipping and learning rate warm-up with a linear scheduler to avoid early overfitting. We used negative log loss as our loss function. And as I mentioned, we had to mask these vert internal tokens in the loss function. So it's usually pretty common to freeze BERT for some epochs and only train the classifier on top and then unfreeze BERT. But what we found during our experiments is we got the best results when both BERT and the classifier were trained from the very first epoch. So we trained every model for 12 epochs and we checkpointed on both the validation F-score and the loss. So it's possible that we, for example, used our model after 3 epochs of training. As I mentioned, we tuned the sliding window size based on the validation set, and all the trainings were performed on a single NVIDIA GPU, a 1070 with a batch size of 4. Okay, so this is our results for English. So our best model was the BERT base, its on-case variation. So we achieved comparable performance to what was reported in the state-of-the-art model. This means a 0.8% absolute, 0.8 absolute difference in terms of overall F-score. And it took 10 epochs of training and 32 predictions per token. In case of the Szeged tree-bank, this might not be a surprise, probably, that our best model was Hubert. We trained it for 3 epochs and used 8 predictions per tokens. And Hubert significantly outperformed the multi-long variation of BERT, which is, I think, kind of expected because Hubert is only trained on Hungarian corpora. So we were curious about the effect of having. We tuned this sliding window on the validation set and then run it through the test set. And we also did experiments on the test set with only using one prediction for a token. And we've seen an increase in F-score of 5% in case of English and 2.4% in case of Hungarian if we used multiple predictions. And as a closing remark, I have two examples from our test set for both the TED Talks dataset and Szeged Treebank. So the things highlighted with green are punctuations that our models got correctly. The yellow ones are wrong punctuations, and the red ones are cases where it plays the punctuation, but it shouldn't have, and it didn't place a punctuation, but it should have. So as you can see, it works pretty decently on these two data sets. And basically, that's what I wanted to talk about. If you have any questions or suggestions, I think we're happy to take them, and I'm happy to answer the questions as much as I can. So thank you.